Welcome, everyone. Today, we'll dive into LeetCode problem number 615, titled Average Salary, Departments versus Company. This problem challenges us to analyze and compare average salaries across departments within a company. It's a fantastic opportunity to sharpen your SQL and data analysis skills. Let's get started. In this problem, your goal is to analyze salary data stored in a relational table and identify departments where the average salary is higher than the overall company's average salary. To solve this, you'll need to calculate the average salary of employees within each department and compare it to the average salary across all employees in the company. The input data is stored in a table called employee, which contains 4 fields: ID, representing the unique identifier for each employee, name, the name of the employee, salary, which is their salary amount, and department ID, indicating the department to which they belong. The structure of this table is provided, and you'll use it to perform the necessary computations and comparisons. To produce the desired output, you need to return a table with 2 columns. The first column, Department ID, represents the ID of the department, and the second column, Average Salary, contains the average salary of that department, rounded to 2 decimal places. However, you'll only include rows in the output where the department's average salary is strictly higher than the company's overall average salary. Let's explore an example to illustrate this. Suppose the employee table contains data for employees across multiple departments, with their salaries and department IDs specified. Based on these records, you will calculate the average salary for each department and the entire company, then filter out departments that don't meet the criteria. In the example provided, the employee table includes 5 employees, each assigned to one of 3 departments. The company's overall average salary is calculated by summing all employees' salaries and dividing by the total number of employees, which gives 3000.00. For each department, you calculate the average using only the salaries of employees within that department. Department 1 and Department 2 both have an average salary of 2500.00, which is below the company average, while Department 3 has an average salary of 5000.00, which is higher. Thus, the output contains only Department 3 with its average salary of 5000.00. In another example, the employee table lists 4 employees, with 2 employees in each of 2 departments. Here, the company's overall average salary is 3000.00. For both Department 1 and Department 2, the average salary is also 3000.00. Because neither department's average salary is strictly greater than the company's average, the output table is empty. This demonstrates that if no department surpasses the company's average salary, the result will contain no rows. This scenario highlights the importance of the strictly greater than condition in the problem. The problem also specifies several constraints and edge cases to consider. The constraints include a guarantee that all salaries are positive integers, IDs are unique, and the size of the data will be manageable within defined limits, up to 10,000 employees and up to 500 departments. Edge cases include situations where there is only one employee in the company, in which case no department can exceed the company average, resulting in no output. Similarly, if all departments have the same average salary, the output will also be empty. On the other hand, if one department has significantly higher salaries than the others, it should be the sole department in the output. Finally, you need to handle extreme salary values, such as very low or very high numbers, while ensuring the results remain accurate and rounded to 2 decimal places. To solve the problem of comparing department average salaries to the company-wide average, we'll start by exploring potential approaches. The brute force method is the most direct and intuitive. It involves calculating the average salary for each department by grouping employee data by department. Separately, we calculate the overall average salary for the entire company. Once we have these 2 sets of averages, we can perform a row-by-row comparison to determine whether each department's average is higher, lower, or equal to the company average. While this method is easy to understand and implement, it has significant drawbacks. The main issue is that the company average might be recalculated repeatedly for each department, leading to redundant computations. This inefficiency becomes particularly problematic with large datasets, where the algorithm's time complexity could balloon to O(n) squared, in the worst case. Although simple, this approach sacrifices performance for ease of implementation, making it less suitable for scalable solutions. A more efficient solution involves leveraging SQL's aggregation functions and joins. In this optimized approach, we first compute the company-wide average salary using a subquery. By treating this value as a constant, we avoid redundant computations. Next, we calculate the average salary for each department by grouping the data using the group by clause. Finally, we use a case statement to compare the department average with the pre-computed company average. This allows us to generate the required output, indicating whether the department's average is higher, lower, or equal to the company-wide average. This method is much more efficient because the company average is computed only once, significantly reducing overhead. However, it does come with a trade-off in complexity. Writing and debugging queries with subqueries and joins may be more challenging for those less familiar with SQL. Additionally, an alternative approach using SQL window functions could be considered for this problem. Using window functions introduces a modern and concise way to solve this problem. Here, we calculate the company-wide average salary directly using a window function, such as a VG, salary, over. This eliminates the need for a subquery, as the company average is computed once across all rows. The department-wise averages can still be calculated using group by, and comparisons can be handled with a case statement. While this approach avoids subqueries and can lead to cleaner SQL code, it has its own considerations. The use of window functions may introduce additional processing overhead depending on the SQL engine being used. Moreover, it is less portable across different SQL dialects, as not all systems fully support advanced window functions. Despite its elegance and modernity, this method may not always guarantee optimal performance in every environment. For these reasons, we focus on a more universally supported strategy that balances efficiency, simplicity, and compatibility. The chosen strategy is the optimized approach using aggregation and joins. This method strikes the right balance between efficiency and simplicity. By calculating the company-wide average salary just once and reusing it for all comparisons, we eliminate redundant calculations and ensure scalability for large datasets. The solution is easy to understand and implement, leveraging standard SQL features that are well supported across most database systems. While it may not be as concise as the approach using window functions, it offers consistent performance and reliability. Additionally, it's more accessible to a broader range of SQL users, making it a practical choice. The trade-off here is minimal, as the slight increase in verbosity is outweighed by the portability and efficiency of this method. Overall, this strategy provides the best combination of performance, clarity, and compatibility for solving the problem effectively. The problem we're tackling involves calculating the average salary for each department and comparing it to the average salary across the entire company. The output we aim for will indicate whether a department's average salary is higher, lower, or equal to the company-wide average. To achieve this, we'll break the solution into a series of logical steps. First, we parse the input data, which consists of records in the form of employee ID, department ID, and salary. From each record, we'll extract the department ID and salary, as these are the key fields needed for computation. Next, we calculate the company-wide average salary. This involves summing up all salaries in a single pass through the data to avoid redundant computations. During this same pass, we'll also count the total number of employees to ensure efficiency. Finally, dividing the total salary sum by the employee count gives us the company-wide average. It's important to handle edge cases, such as when there are no employees, by returning a default value of 0 for the average salary. Now that we have the company-wide average, the next step involves computing the average salary for each department. To do this, we use a dictionary to group salaries by department. The dictionary is structured with department IDs as keys and their corresponding sum of salaries and employee counts as values. For each record, we retrieve the department ID and salary, then update the department's total salary and employee count in the dictionary. Once the data is aggregated, we calculate the average salary for each department by dividing its total salary by its employee count. After computing the department averages, we compare them to the company-wide average. For each department, if its average is higher, we mark it as higher, if it's lower, we mark it as lower, and if they're equal, we mark it as equal. These results are stored as a list of tuples, where each tuple contains the department ID and its comparison result. Finally, this list is returned in the required format, completing the process. The algorithm is designed to be highly efficient. By calculating both the total salary and employee count in a single pass, we optimize the computation of the company-wide average, reducing the time complexity. Similarly, the use of a dictionary for grouping department data ensures constant time access and updates, avoiding the need for nested loops or multiple scans of the data. Special attention is given to handling edge cases, such as when there are no employees or when a department has no salaries. These situations are carefully managed to avoid division errors or producing incorrect results. In terms of data structures, the input is a list of records for efficient sequential access. A dictionary is used for aggregating department data, ensuring fast updates and lookups. The final output is a list of tuples, which makes it easy to interpret the results. The algorithm's time complexity is O(n), where n is the number of input records, and its space complexity is O(d), where d is the number of unique departments. It's crucial to consider edge cases to ensure the algorithm works under all possible scenarios. If the input data is empty, meaning there are no employees, the output should simply be an empty list. For cases where there's only one department, the comparison logic should correctly identify whether its average salary is higher, lower, or equal to the company-wide average. Additionally, we need to handle situations where a department has employees with zero salaries. For such departments, the algorithm must still compute the average correctly without running into division errors. Let's look at an example to clarify the process. Suppose we have the following input records: an employee from the HR department earning $5,000, another from engineering earning $7,000, and a second HR employee earning $6,000. In this case, the algorithm will calculate the company-wide and department-wise averages and return the comparison results as output. In this example, the company-wide average salary is calculated as the sum of all salaries $5,000, $7,000, and $6,000 divided by the total number of employees, which is 3. This gives us a company-wide average of $6,000. For the HR department, the total salary is $5,000 plus $6,000, giving $11,000, divided by 2 employees, resulting in an average of $5,500. Since $5,500 is less than the company-wide average of $6,000, HR is marked as lower. For engineering, the total salary is $7,000, and with only one employee, the average is $7,000. Since $7,000 is greater than $6,000, engineering is marked as higher. The final output is a list of tuples: HR is lower, and engineering is higher. This example demonstrates how the algorithm efficiently computes and compares averages using a single-pass aggregation technique and minimal data structures. By leveraging dictionaries for grouping and lists for output, the solution remains both clear and efficient. Here, we begin by importing the default dict class from the Collections module. This will help us manage and organize salary data for each department. Inside our solution class, we define a method named average salary departments versus company that takes employee_data as input. This data is expected to be a list of lists, where each sublist contains an employee's ID, their department ID, and their salary. First, we create a default dict called department_salary to store the total salary and employee count for each department. Each value in this dictionary is initialized as a list containing 2 zeros, one for the total salary and one for the employee count. Additionally, we initialize 2 variables, total_company_salary and total_company_count, to keep track of the overall salary and number of employees across the entire company. Next, we iterate over the employee_data. For each record, we extract the department ID and salary. We update the corresponding department's total salary and employee count in the department_salary dictionary. Simultaneously, we increase the total_company_salary and total_company_count by adding the current employee's salary and counting them. Once this loop completes, we calculate the company's average salary by dividing the total salary by the total count. This value, company_average_salary, will serve as a benchmark to compare against the average salaries of individual departments. Finally, we prepare an empty dictionary called result to store the comparison results for each department. For now, we're iterating through the department_salary dictionary, and for each department, we calculate its average salary by dividing the total salary by the employee count. We compare this department average with the company's average and classify it as higher, lower, or equal accordingly. If the department's average salary matches the company's average, we assign the value equal to that department in the result dictionary. With that, our logic for comparing department averages to the company's average is complete. The method then returns the result dictionary, which provides a mapping of each department ID to its comparison result, indicating whether its average salary is higher, lower, or equal to the company's average. To illustrate how this method works, we provide an example. We create an instance of the solution class and call the average salary departments versus company method with a sample dataset. This dataset consists of 5 employees, each with their respective IDs, department IDs, and salaries. When we pass this data to the method, it processes the information and outputs a result that shows how each department's average salary compares to the company's overall average. This example allows us to see the method in action and verify its correctness. By running the code, we can observe how the logic handles different scenarios and provides clear insights into the salary distributions across departments. To begin, we import the necessary libraries and create our solution class. Inside the method average salary departments versus company, we start by initializing 2 key data structures. The first is a map called department salary, where each department ID is mapped to an array that stores the total salary and the number of employees in that department. The second is to track the total salary and employee count for the entire company. Next, we iterate through the employee data provided as a list of integer arrays. Each record contains the employee ID, department ID, and their salary. For each entry, we update the department's total salary and employee count in the map. Simultaneously, we update the overall company's salary and employee count. After processing all the records, the map will hold cumulative salary data for each department, while the company-wide totals will help us calculate the average salary for the entire organization. Using these totals, we calculate the company-wide average salary by dividing the total salary by the total number of employees, casting to a double to ensure precision. This average will serve as the benchmark for comparing each department's performance. Now, we iterate through the entries in the department salary map to calculate the average salary for each department. For every department, we retrieve its total salary and employee count, then compute the average by dividing the total salary by the count, again ensuring precision by casting to a double. Once we have the department's average salary, we compare it with the company's average. If the department's average is higher, we record the department's ID in the result map with the value higher. If it's lower, we record lower, and if it's equal, we record equal. This comparison allows us to categorize each department based on how their average salary stacks up against the company-wide benchmark. The result map, which associates each department ID with its category, will ultimately be returned as the output of this method. Finally, in the main method, we create an instance of the solution class and supply example data to test our implementation. The example dataset contains records for multiple employees, each specifying their employee ID, department ID, and salary. We invoke the average salary departments versus company method with this data and store the resulting map. This result map, which indicates whether each department's average salary is higher, lower, or equal compared to the company's average, is then printed to the console. This step provides a clear demonstration of how the solution processes input data and produces meaningful insights about salary comparisons at the department level. To start solving the problem, we use the given input data, which is a list of employee records where each record contains an employee ID, a department ID, and the employee's salary. We begin by initializing 3 variables, department_salary as an empty dictionary to track total salaries and counts per department, total_company_salary as 0 to accumulate the total salary across the company, and total_company_count as 0 to count the total number of employees. Next, we iterate through each employee record. For the first record, 101, 50,000, we identify that the employee is in Department 101 and earns a salary of 50,000. We update department_salary to reflect this by setting Department 101's total salary to 50,000 and its employee count to 1. This ensures we're starting to track department-level data. Additionally, we increment the company's total salary to 50,000 and the employee count to 1, capturing the overall company metrics so far. As we continue processing the employee data, we move to the second record, 101, 60,000, where another employee in Department 101 earns a salary of 60,000. We update Department 101's total salary to 110,000 and its employee count to 2 in Department_salary. The company's total salary increases to 110,000, and the employee count becomes 2. Next, 102, 70,000, an employee in Department 102 earns 70,000. We add Department 102 to Department_salary, setting its total salary to 70,000 and its count to 1. The company's total salary grows to 180,000, and the count increases to 3. 102, 80,000, another employee in Department 102 earns 80,000. We update Department 102's data to a total salary of 150,000 and a count of 2. The company's metrics are updated as well, with a total salary of 260,000 and a count of 4. Finally, 103, 55,000, we add Department 103 to Department_salary, setting its salary to 55,000 and its count to 1. The total company's salary reaches 315,000, and the count becomes 5. With all records processed, we now have complete salary and employee count data for both the departments and the company. To calculate the company's average salary, we divide the total company salary of 315,000 by the total employee count of 5, yielding a result of 63,000. This value serves as the benchmark for comparing department averages. Next, we calculate the average salary for each department. For Department 101, the total salary of 110,000 is divided by 2 employees, resulting in an average of 55,000, which is lower than the company average. Department 102's average salary is 150,000 divided by 2, resulting in 75,000, which is higher than the company average. Finally, Department 103 has an average salary of 55,000 for its single employee, which is again lower than the company average. Based on these comparisons, we determine that Department 101 is lower, Department 102 is higher, and Department 103 is lower. The result is encapsulated in the output dictionary: 101, lower; 102, higher; 103, lower. In the next example, all employees earn the same salary of 60,000. We initialize the required variables as before, Department_salary as an empty dictionary, and both total_company_salary and total_company_count as 0. Starting with the first record, 201, 60,000, we add Department 201 to Department_salary, updating its total salary to 60,000 and its count to 1. The company's total salary becomes 60,000, and the count increases to 1. For the second record, 201, 60,000, another employee in Department 201 earns 60,000. We update Department 201's data to reflect a total salary of 120,000 and a count of 2. The company's total salary increases to 120,000, and the count becomes 2. Finally, 202, 60,000, an employee in Department 202 earns 60,000. We add Department 202 to Department_salary, setting its salary to 60,000 and its count to 1. The company's total salary grows to 180,000, and the count reaches 3. At this point, we've gathered all the data for this example. To compute the company's average salary, we divide the total salary of 180,000 by the employee count of 3, resulting in an average of 60,000. This matches the salary of every employee in the input data. Next, we calculate the department averages. For Department 201, the total salary of 120,000 divided by 2 employees gives an average of 60,000, which is equal to the company average. Similarly, Department 202's average salary is 60,000 for its single employee, which is also equal to the company average. Since all department averages are equal to the company-wide average, the output for this example is 201 equal 202 equal. In the final example, all employees belong to a single department, Department 301, with varying salaries. We initialize Department_salary as an empty dictionary, and both total_company_salary and total_company_count as 0. For the first record, 301, 40,000, we add department 301 to department_salary, setting its salary to 40,000 and its count to 1. The company's total salary becomes 40,000, and the count becomes 1. Next, 301, 60,000, another employee in Department 301 earns 60,000. We update Department 301's data to a total salary of 100,000 and a count of 2. The company's total salary increases to 100,000, and the count becomes 2. Finally, 301, 50,000, another employee in Department 301 earns 50,000. We update Department 301's data to reflect a total salary of 150,000 and a count of 3. The company's total salary grows to 150,000, and the count reaches 3. Now we have all the data needed for calculations. To determine the company's average salary, we divide the total salary of 150,000 by the employee count of 3, resulting in a company average of 50,000. For Department 301, the total salary of 150,000 divided by its 3 employees also yields an average of 50,000. Since this department's average matches the company average, the department is categorized as equal. Thus, the output for this example is 301 equal. To analyze the time complexity of the function average salary departments versus company, we can break it into 3 main steps. First, we process the employee data. Here, we iterate through the employee_data list, which contains n employees. For each employee, we update the total salary and the count for their respective department, as well as the total salary and count for the entire company. Since this involves a single loop over the employee list, this step takes n time. Next, calculating the company's average salary involves a simple division operation, which is constant time, or O1. Lastly, we compare department-level salaries with the company average. This step involves iterating over the department_salary dictionary, which contains 1 entry for each department. If there are D departments, we perform O(D) operations, as each department's average salary is calculated and compared with the company average. Together, these steps give us a detailed breakdown of the function's time complexity. Now, when we combine these steps, the overall time complexity becomes O(n) plus O(1) plus O(d). Since constants like O(1) do not affect overall growth, this simplifies to O(n) plus d. In the best-case scenario, where all employees belong to the same department, d equals 1, and the complexity reduces to O(n). In the worst case, where each employee belongs to a unique department, d equals n, and the complexity becomes O(2n), which simplifies back to O(n). Regardless of the scenario, we can conclude that the time complexity is O(n), since the number of departments, d, will always be less than or equal to the number of employees, n. Moving on to space complexity, the input data, employee_data, requires O(n) space as it contains n entries, each with 3 values. Additionally, we use auxiliary data structures, such as the department_salary dictionary. This dictionary stores 1 entry per department, and if there are D departments, it requires O(d) space. Each entry contains 2 integers, making the total space proportional to 2d, which simplifies to O(d). Lastly, the result dictionary, which stores the comparison results for each department, also requires O(d) space. Beyond these dictionaries, we use a few other variables, such as total_company_salary, total_company_count, and company_average_salary. These are scalar values and require constant space, or O(1). Adding everything together, the total space complexity is the sum of the input storage, auxiliary data structures, and other variables, O(n) plus O(d) plus O(d) plus O(1), which simplifies to O(n) plus d. Since d is always less than or equal to n, the space complexity simplifies further to O(n). When we compare this optimized solution to a naive approach, the efficiency becomes even more apparent. A brute force method might involve iterating through the dataset repeatedly for each department to calculate department averages. This would result in a time complexity of O(n*d), which is highly inefficient for large datasets. In contrast, the proposed solution aggregates salaries and counts in a single pass using dictionaries, achieving a significantly better time complexity of O(n). To summarize, the time complexity of the solution is O, n, in all cases best, average, and worst, since the number of departments, d, is always less than or equal to the number of employees, n. The space complexity is also O, n, as the solution only requires space proportional to the input size and the number of departments. This approach is highly optimized compared to a brute force solution, leveraging dictionaries to aggregate and compare salaries efficiently. By reducing repeated computations and minimizing auxiliary space usage, this solution ensures scalability and performance for large input data sets. One common mistake developers make when solving this problem is forgetting to group salaries by department before calculating the average. Instead of analyzing data within individual departments, they calculate the overall company average and then attempt to compare individual salaries directly. This approach leads to logical errors because it ignores the departmental structure of the data. To avoid this, use SQL's group by clause or similar grouping logic in Python or Pandas to ensure averages are computed for each department separately. Another common issue arises from integer division, especially in languages like Python 2 or Java. When you divide integers directly, the result is truncated, causing precision errors. Always cast one of the operands to a float to ensure accurate division. Lastly, edge cases are often overlooked. For example, departments with only one employee or departments missing data entirely can cause unexpected behavior. Validating that each department has sufficient data, like filtering out departments with fewer than 2 employees, will help prevent these issues. Performance inefficiencies can also be a significant challenge, particularly when working with large datasets. Using nested loops or performing redundant calculations can drastically increase time complexity. Instead, aim for an O(n) solution by leveraging hash maps or dictionaries for efficient aggregation. Another pitfall is misunderstanding the core requirement of the problem. Some candidates mistakenly compare individual salaries to the overall company average rather than comparing them to their respective department averages, which is the actual requirement. To avoid such misunderstandings, it's crucial to carefully reread the problem description, paying attention to specifics, and clarify any ambiguities before proceeding with your solution. This problem is designed to test your ability to work with aggregate data effectively. Skills like grouping, filtering, and calculating metrics such as averages are frequently required in data-related roles. A key area to focus on is optimization. For example, calculating the company average once and reusing it throughout your solution can save a significant amount of computational effort. When presenting your solution, be prepared to explain trade-offs. If using SQL, discuss the performance implications of the group by clause and how database indexing could improve speed. For Python-based solutions, highlight the differences between using pandas for simplicity and native dictionaries for better performance when working in memory. Finally, edge case awareness is critical. Be ready to explain how your solution handles scenarios like missing data, departments with only one employee, or extremely large datasets. These considerations can help you stand out in an interview. For further practice, related problems like LeetCode number 177, number 626, number 601, and number 184 can provide additional insight into similar concepts. When considering alternative approaches, using SQL is often a straightforward and maintainable choice. It allows you to write concise queries for grouping and aggregating data, but it does rely on database execution, which means performance depends heavily on the database's optimization capabilities. A Python dictionary-based approach is another option. In this method, you can aggregate salaries for each department into a dictionary, calculate department averages, and compare them to the pre-computed company average. This approach is efficient and works well for in-memory operations, but it may not scale effectively for extremely large datasets. Finally, a pandas data frame approach offers a high-level, readable solution. Using methods like group by and mean, you can easily calculate department averages and perform vectorized comparisons against the company average. While pandas simplifies the implementation, it can be more memory-intensive, especially for massive datasets. Each of these methods has its trade-offs, so choose the one that best aligns with the specific requirements and constraints of your task. Great job following along. To recap, we successfully tackled problem number 615 by calculating departmental and company-wide salary averages using SQL. You've practiced essential SQL skills and learned key optimization techniques. If you found this helpful, be sure to like, subscribe, and stay tuned for more coding solutions. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!